Alright, so we're recording the class now. So the last class that we had, we were discussing VAR models. Okay, and since it's been a long time, I will have to cover the introductory portion again. So I'm guessing that most of you will not remember it. I haven't shared the notes also. So just think of it as a refresher. Some of you might be able to recall it as we are discussing. All right, so we are going to discuss VAR models. Some people also refer to it as VAR models. Okay, it's essentially the same thing, just the pronunciation is different. So VAR models are vector autoregressive models, and they are also used for forecasting purposes. If you all have any doubts or questions in between, please feel free to stop and ask me. So VAR models are basically used for forecasting purposes, and the main objective of such models is to study the interrelationships between variables and see whether they affect each other. Okay, so in most of the time you will find that in certain models you look at one-way effects between variables, that maybe xt affects yt, okay, not the other way around. But in certain cases there could be a situation where xt affects yt and yt also affects xt. Okay, so to allow for such feedback effects or bidirectional effects between variables, we usually use VAR models and then estimate such models, then use them for forecasting purposes. So first we'll begin with a very simple bivariate model. Okay, I'll try and go through this quickly since we've discussed this in the previous class. So this is a very simple bivariate system where you have two variables, two time series variables, yt and zt. Okay, and the reason that we're using a VAR model is because of the structure of the model, which allows yt to be affected by zt and zt to be affected by yt. Okay? Now, if you look at the first equation here, you'll find that yt depends on its own lag, the first lag, and it also depends on the first lag of zt. Okay? And at the same time, you'll find that zt has an impact on this in the same time period on yt. Okay? So this is called a contemporaneous effect that zt has on yt. It's happening in the same time period, not with a lag. Now, similarly, if you look at equation 2, here you'll find that again zt depends on the first lag of yt as well as its own first lag. And in turn, here also you notice the same thing, that here yt has an impact on zt in the same time period again. So this is the contemporaneous impact of yt on zt, which is captured by this coefficient b21. Okay? Now, when we propose such a model, which has these two equations and allows us to study the interrelationships between yt and zt, we are making certain assumptions here. Okay? One is that both yt and zt are stationary. So whenever we are estimating VAR models, we will have to go through the preliminary steps of actually checking for stationarity of the variables. Once you have done that, then you can proceed with the VAR model. Okay, so both yt and zt are assumed to be stationary here, since we are looking only at theory. Okay, we are assuming that they are stationary. Then epsilon yt and epsilon zt, which you find here, okay, in equation 1 and 2, are white noise error terms with standard deviations of sigma y and sigma z respectively. So when we are saying that these are white noise error terms, okay, it means that the expectation of epsilon yt and epsilon zt, that will be equal to 0. So they have a mean of 0, they have some constant variance, and their covariances are equal to 0. Okay, they are uncorrelated with each other. So this is laid out in the third assumption here, that epsilon yt and epsilon zt both are uncorrelated. Okay, But one thing is important to note here, that if B12 is not equal to 0, okay, that is this coefficient, then epsilon zt has an indirect contemporaneous effect on yt. Okay. Now the effect it has on yt is obviously through zt. Since epsilon zt appears in this equation for zt, okay, you will find that because of this, although it does not appear in equation 1, it still has an indirect impact in the same time period again on yt. Okay. I hope this is clear to all of you. But if B12 here is equal to 0, okay, then this will not have an indirect contemporaneous effect on yt. Only if this coefficient is not equal to 0 will this error term here, epsilon zt, have an indirect contemporaneous effect on yt. Now similarly, if this coefficient here, B21, is not equal to 0, okay, then again, if you use the same logic, although epsilon yt does not appear in equation 2, okay, it appears indirectly in the form of yt. Okay, since yt has this term in its equation, it appears indirectly in equation 2. So similarly, epsilon yt will have an indirect contemporaneous effect on zt here. Okay, so it will affect zt in the same time period, but only indirectly. Okay. So this has been stated here in this note, that if B12 is not equal to 0, then epsilon zt has an indirect contemporaneous effect on yt, and if B21 is not equal to 0, epsilon yt has an indirect contemporaneous effect on zt. Okay. Now using matrix algebra, we can rewrite these two equations, equation 1 and 2, okay, in the form of matrices here. So here what has been done in this equation is yt and zt, since they are also appearing on the right hand side, these terms have been shifted to the left hand side. Okay, and then the matrix has been created. So here you'll find that once you shift the terms, you're able to create this coefficient matrix here. Okay, and you're able to shift all these variables only to the left hand side. Okay, yt and zt, which are the endogenous variables in our model. Okay, since their values are being determined within the model, they are endogenous variables. Now here, these are the constant terms. So this is a vector of constant terms. Then these are the coefficients associated with the lagged values, okay, with the first lag of yt and zt. And these are the structural error terms of our model. So we can simplify the notation here further and rewrite this again as B. Okay, we can denote this matrix here by B, this vector here of the endogenous variables by xt. Then we can denote this vector of the constant terms by tau naught. Similarly, this matrix can be denoted this way, and this will be xt minus 1, okay, since it's the lag of these endogenous variables. And here, to denote these structural error terms, the vector of these structural error terms, you have epsilon t here. Okay. So here we've explained what each of these terms mean, what is B, what does this matrix B denote, and so on. Any doubts or questions so far? Okay, I'm guessing you don't have any doubts or questions. So let's move on to the next page. At any point, if you have doubts, please make sure that you stop and ask me. Okay. Now, if we 3 multiply the previous equation that we saw by B inverse, okay, we can get the VAR model in what is known as the standard form. So this is the typical form in which the var model is represented. Okay? So if we pre-multiply that previous equation that we saw by B inverse, we can get the var model in the standard form, and it's denoted this way. Okay? Here, since if you're multiplying B inverse into B, you're going to get an identity matrix. Okay, so that term vanishes. So you simply have xt here, then A naught. Okay, so this represents the multiplication of B inverse with the vector of constant terms. Okay. Then A1 represents the multiplication of B inverse again with the matrix which was associated with the lagged values of those endogenous variables. Okay. So this way we can rewrite the var model in its standard form, what is known as the standard form. Now again we define certain elements. Okay. So we define ai naught as the element I of vector a naught. Okay. So for example, a1 naught refers to the first element in that matrix. Okay. The first constant term which will appear. Then similarly, aij refers to the element in the ith row and jth column of a1. Okay. Similarly, eit denotes the element I of vector et. Okay. Now, once you multiply it, later on, once I share the notes with you all, try and multiply it out. I think it's given elsewhere in this set of notes, but try and multiply it out so that you know exactly what those terms are, what A1 naught is, what A2 naught is, similarly what A1 2 is. Okay. Now, if you use this notation defined above, again you can rewrite this var model in the standard form by expanding each term. Okay, so we can again decompose it into the two equations, one for each of the time series that are there in this var model, and we can write it out in a more expansive way. So here what you'll notice in equation 4 and 5, okay, I had asked you all this in a previous class. Let's see if you can spot it again. Okay, equation 4 and 5 are different in a certain way from the first two equations that we came across. Okay, when I
Now
showed you the
ZT,
first and second equation in the set of notes that we saw today, what is the difference between 4 and 5 and 1 and 2? Okay, let me just put up 1 and 2 also so that you can compare. Okay, so this is equation 1 and 2. And this is 4 and 5. Can anyone tell me what is the difference between the two sets of equations?
ma'am, now YT is not directly related with ZT.
If you're typing in the chat box, I won't know. Okay, so try and speak up. Since I'm sharing this, I won't be able to tell if you've typed anything in the chat box.
Am I audible?
Ma'am, I think you can't
Any,
hear us.
yeah, Neil and some, I think you have to unmute yourself.
Ma'am,
You're trying to
can you
answer,
hear
right?
us?
Well, I'm not able to hear you all for some reason. Let's see if. Well, I'm not able to hear you all. I don't know what the problem is. So, anyway, fine. You can type in the chat box. That ZT term is missing. All right, let me try and rejoin. Let's see if. Okay, I'm just stopping for a minute and I'll rejoin. Let's see if that fixes the issue. All right, please don't leave the class. Yes, okay, yeah. Okay, now you can speak. Sorry, I had, I think, put it on mute. Yeah, somebody answered. The ZT term is missing, right? So can you
Yes,
tell
ma'am.
me?
Now, YT is not directly related with ZT, like the equation 1 and 2.
Okay. Anyone else? Can you put it in a slightly different way? You're right, but if you can state it in a slightly different way, it'll help.
Ma'am, we have taken care of the contemporaneous effect, basically. So we can
Yeah.
solve these two equations independently.
Okay. Yeah, that's good. Okay, so basically you've eliminated the contemporaneous effect here somehow. Okay, so if you look at 4 and 5, okay, equation 4 and 5, what you'll see is that on the right hand side you have only predetermined variables. Okay, variables whose values will be known in advance in some sense. Okay? So because of this, you can actually use OLS and run the regressions now. Okay? So earlier, when you had the contemporaneous variables, for example, when in equation 1 you had zt appearing on the right hand side, in equation 2 you had yt appearing on the right hand side. There, because of the fact that zt had epsilon zt appearing indirectly in equation 1, okay, and also in equation 2 epsilon yt was appearing indirectly through yt, which was there on the right hand side of equation 2. Okay, so because of that, you will find that it is very likely, I'm showing you equation 1 and 2 again, it's very likely that the errors across equations would have been correlated in some sense, okay, or the regressors would have been correlated with the error terms, okay, which is not a good thing to happen in any uh, regression model. We want the errors and the error terms appearing in the regression to be uncorrelated with the regressors. Okay, so here if these contemporaneous variables appear on the right hand side, then there's a problem in using OLS directly on the equations. Okay, so because of this, we kind of purge the model of these contemporaneous variables through certain transformation, okay, by using the B inverse matrix. And then we are able to run the regression because now the right hand side has only predetermined variables which will not be correlated with the error terms. Okay. So now if you look at the system of equations represented by 1 and 2, okay, uh, okay, 1 and 2 are referred to as either the primitive system or what is known as a structural var. So any structural model generally, it has endogenous variables appearing even on the right hand side. Okay? So in equation 1 and 2, you also had zt and yt appearing on the right hand side. Now if you look at 4 and 5, you don't have any of the endogenous variables, which is yt and zt appearing on the right hand side. You have their lagged values appearing, which is a huge difference here. Okay. So because of that, 1 and 2, okay, that system of equations is known as a structural var or the primitive system, excuse me, while 4 and 5 are called a var in the standard form. Okay? So if you look at the standard form, in certain models, it's also known as a reduced form equations, where on the right hand side, you will have only predetermined variables appearing or variables which are exogenous. Okay? So this 4 and 5 is called a var in the standard form. Now in 4 and 5, okay, if you multiply out the terms that were appearing earlier, I'll leave you to do it after the class. Okay. So if you look at E1t, the error term which appears in equation 4, okay, it will be equal to this term. Okay. Here, this is the determinant of your B matrix. So if you look at E1t and E2t, both are composed of the structural error terms. So you have epsilon yt as well as epsilon zt appearing in equation 6 and 7. So they are made up of the structural error terms that you saw in equation 1 and 2. Now since epsilon yt and epsilon zt are white noise processes. Both E1t and E2t have zero means, constant variances, and they are individually serially uncorrelated. Okay, so there will be no autocorrelation in E1t and in E2t. Okay, now we are proving these things in the next page. The same thing, that E1t and E2t have zero means, constant variances, and that they are individually serially uncorrelated. Let me know if you have any doubts or questions at any point of time. Okay.
Yes, ma'am. If we have anything, we'll let you know.
Okay. Okay, so here we are simply verifying it. I won't explain this portion. You can just take a look at it. Okay, since expectation of epsilon yt and epsilon zt will be equal to 0, even expectation of E1t is equal to 0. Okay. Then you can see that they have constant variances and the autocovariances are equal to 0. You can do the same sort of derivation for E2t and you will find the same result, that E2t has a zero mean, constant variance and zero autocorrelation. Okay. But one thing is important to note here, that E1t and E2t are correlated with each other. Okay. And if you look at the covariance of these two terms, you will find that it is equal to this. Okay, I'm just giving you a moment to look at it carefully. Here we are simply writing out what is E1t and E2t. Okay. Since the means are 0, you'll simply be multiplying these out with each other. Okay. Now in general, okay, this equation will not be equal to 0 if you look at equation 9. So the two shocks will be correlated. Now only in the special case where B12 is equal to B21 and both are equal to 0, the shocks will be uncorrelated. Okay. So basically we are saying that if there are absolutely no contemporaneous effects in our VAR model, only then these two shocks, E1t and E2t, will be uncorrelated with each other. Otherwise, they are bound to be correlated with each other. Okay. Now we can also define what is known as the variance covariance matrix of E1t and E2t shocks. Okay. So it is denoted by this term sigma here. So the elements of sigma are the variance of E1t and E2t along the diagonal, okay, and the off diagonal elements will be your covariance terms. Okay. Okay. Now you will find, if you look at the elements of sigma, okay, all the elements you found that when we derived the variance of E1t, it was time independent. Okay, it did not depend on time at all. So we can denote this matrix itself, sigma, in a more compact form this way. Okay. So this simply denotes the variance of E1t, this denotes the variance of E2t, and this is the covariance between E1t and E2t. Okay. These two will be equal to each other, sigma 1, 2 and sigma 2, 1. Now, when we try to actually estimate our VAR model, we are going to come across a particular problem. Okay. So before we discuss what exactly that problem is, it's the problem of identification. But before we get into that, let's just look at a more general notation. Okay. So earlier we were looking at a first order var model where you were including only the first lag of yt and zt as explanatory variables or on the right hand side of the equation. Okay. Now suppose we want several lags or a pth order var model. Then in that case, we can write this multivariate generalization of an autoregressive process. Also earlier we were looking at a simple bivariate var model where you had only two time series that we were considering, yt and zt. Suppose you have n variables in your system instead of only two variables. Okay, so to denote such a situation, we can use this multivariate generalization of the var model itself, which can incorporate several lags of each of those variables. Okay, so here we denote the system of equations using equation 11. Okay. So I think we had discussed up to this point. Now xt here is basically an n into 1 vector which contains each of the n variables included in the var model. So this will be your vector of endogenous variables or all the variables whose interrelationships you want to study through your var model. Then a naught will be a vector of all the intercept terms. So you will have all your constant terms in the vector a naught here. And there will be n such constant terms. That's why it's an n into 1 vector. Okay, then if you look at ai, here this is a matrix, okay, of coefficients, and it's an n by n matrix of coefficients. Now, I think in the previous class I had asked you all why is it exactly an n by n matrix. Okay, so if you notice here in this equation, there are p lags of each of the variables here, okay, in your model. So suppose, let's say instead of two variables, let's say there are four variables. So each of those four variables have p lags. Okay. Now if you take only this one, okay, if you take only a1, since ai has been denoted here, if we take only a1, in a1 you will have n endogenous variables again. Okay. So basically you have your n time series variables, and each of them will have these n coefficients associated with the first lag of each of those variables. Okay, so because of that, ai or a1 will be an n by n matrix of coefficients. Okay, I hope this is clear to all of you. So each of these will be n by n matrices of coefficients, each associated with the particular lag that we are considering. Okay. Then et here is an n by 1 vector of error terms. So since there are n time series or endogenous variables in a var model, you will have associated with them n error terms. Okay. Now, if you notice, compared to what we've learned in ARIMA modeling, if you look at the focus of ARIMA models, they try and obtain very parsimonious models where you try and cut out the insignificant lags and try to make your model as simple as possible and include as few regressors as possible in the ARIMA models. Okay? So the principle of parsimony is very important in ARIMA models or when you're using the Box-Jenkins methodology. Okay? But in a var model, the focus is completely different. So it does not really matter if you have too many variables and too many lags in your var model. Okay, since the focus on in any var model is to look at the relationship between the variables, okay, so the researcher or the econometrician will not really be concerned about having too many lags in the model. Okay, so just read this for a moment. I'm getting a call. I'm sorry, I need to take the call. I'll be right back. All right. Sorry about that. So let's come back to this. Okay. So here in a var model, the focus will be on looking at how the variables are related to each other, or how one variable affects the other variable. Okay. So that will be the primary interest. Yeah, sorry. Okay. Yeah. So parsimony will not be important here. Okay, so because of this, it's very likely that your var model will be over parameterized. You will have too many coefficients that you are going to estimate. And most of the time you might find that your coefficients are also insignificant, but it's not really important in a var model, because there are certain other tools that we use in a var model which are usually more important than simply estimating the values of the coefficients. Also, if you have an n variable var model where maybe you have 5 variables or 7 variables, of course you will not be discussing the coefficient values of the p lags. Okay, so the coefficient values will not be so important. It will not be a terrible thing even if they are insignificant, okay, the coefficients. But what we are interested in is certain other tools that we'll learn about as we go through this class. So it's all right if your model is over parameterized. Okay. Okay, so since the right hand side of equation 11 contains only predetermined variables and the error terms are assumed to be serially uncorrelated and they have constant variance, okay, so we can easily use OLS to estimate each equation in the system. So this is what I was saying earlier. So if you simply pick up equation 1 and 2, the equations that we began with, that are referred to as the primitive system or the structural var, you cannot use OLS on them directly because the regressors would have been correlated with the error terms. Okay. So here, once you transform the model by using B inverse, putting the var model in the standard form, and you actually start working with equation level, now you are able to use OLS on those equations and actually estimate the coefficients of your var model. Because now your right hand side has only predetermined variables and the error terms are serially uncorrelated, plus they will not be correlated with your regressors. Okay. Sorry, this is a little blurred, but I hope you're able to read it. Okay. Now, since A naught contains n parameters, okay, so your vector of constant terms or intercept terms has n parameters, and each AI matrix contains n square parameters. Okay, so each of those AI matrices were n by n matrices, right? Okay. And since each of those matrices, again, you have p lags of your endogenous variables, so there will be pn square such coefficients to estimate. So you have n coefficients, which are your intercept terms or constant terms in each of the equations, plus you have pn square coefficients, which are associated with the lagged values of your time series variables. So together they make up a total of n plus pn square coefficients that need to be estimated. So you can clearly see that your var model is likely going to have a very large number of parameters or coefficients. But the OLS estimates will be consistent and asymptotically efficient. They will have minimum variance amongst all the class of linear unbiased estimators. Now we come to the problem that I had mentioned earlier, that when we actually try to estimate the var model, we are still going to have a certain problem that we will come across. So what is that problem? Okay. This is known as the problem of identification. Okay. Since we transformed our var model, put it in a standard form, But what we would ideally want to do is try and find out the values of the parameters that are there in our structural model. Okay, we began with the structural model, and ideally we would like to make sure that we actually are able to get the estimates of the parameters from that model, the model that we started out with. Okay. But is it possible to actually recover the parameters of the structural VAR from our estimates of the model in the standard form? Okay. Now, due to feedback between yt and zt, we cannot estimate 1 and 2 directly. Okay, this is what I had mentioned earlier, that since the contemporaneous effect is there in equation 1 and 2, you will not be able to estimate equations 1 and 2 directly, since the regressors and error terms will be correlated. Okay? So instead, we try and work with the VAR model in the standard form. Now, is the primitive system identifiable given the OLS estimates of the VAR model in the form of equation 4 and 5? Okay. So can we actually recover or get unique estimates of all the parameters from our primitive system or from equation 1 and 2? Can we get unique estimates of all those parameters if we estimate the VAR model that was there in equation 4 and 5, the VAR model in the standard form? Okay. Now we cannot actually do this unless we impose certain restrictions on the primitive system. Okay. So we will not be able to actually get estimates of all the structural parameters by estimating 4 and 5 unless we impose certain restrictions on those structural parameters. Okay, now why does this happen again? You already understood that that contemporaneous effect creates certain problems. But apart from that, if you look at the numerical problem, you'll be able to understand why we cannot get estimates of the structural parameters. Okay, so first what we need to do is compare the number of parameters that are there in the primitive system and the number that you get from the estimated VAR model. Okay. Okay, so this has been cut off, but I'll be able to tell you, and I think you can also figure out what has been cut off. So these are the coefficients that you're able to get from your estimated VAR model. That is the VAR model in the standard form. You'll get A1 naught, A2 naught. These are the intercept terms. A11, A12. This is the coefficient associated with the lag of yt. Okay, coefficient associated with the lag of zt. Similarly, this is, I think you can figure out what these two terms are. So these are the coefficients that you can recover from the estimated VAR model. Then you have the variance of E1t, variance of E2t, and covariance E1t and E2t. Okay, so if you check how many parameters there are that you have been able to estimate using the VAR model in the standard form, there are 9 such parameters. Okay. But if you look at the primitive system now, how many parameters are there in the primitive system? Okay. You have the coefficients, these constant terms. Then you have the coefficients or parameters associated with the lagged variables. Then you have these contemporaneous effect coefficients, and you have the standard, the standard errors or standard deviation of the structural error terms. Okay, so you have a total
Could you
of,
zoom in one more level?
sorry,
Could you zoom in by one more level?
yeah, is this better?
Yes, ma'am.
Okay. So you have here 10 parameters. Okay, this here B21 has been cut off, and this is variance E1t. Okay, in case you're trying to figure it out. So here you have a total of 10 parameters. Okay, you have 2 plus 4, another 2 here. So 8 plus 2, 10. Okay, so you have 9 parameters that you've been able to estimate from the VAR model in the standard form. And here you have 10 parameters that are structural in nature and that you wanted to find out. Okay, so obviously you cannot recover 10 parameters on the basis of 9 parameters that you have been able to estimate. Okay, So it is necessary for us to actually restrict one of the parameters in the structural model so that we can actually identify the primitive system. So when we are saying identify, we mean that can you actually get estimates or recover unique estimates of the structural parameters from the estimated var model, which is the var model in the standard form. So unless we restrict one of the parameters, that is one of these structural parameters, it is not possible to identify the primitive system, and equations 1 and 2 will be under identified. Since there are more number of structural parameters that we need to estimate, but we have fewer estimates available from the var model in the standard form. That's why it's known as under identification. Okay? You will not be able to recover unique estimates of the structural parameters. Okay, so this is the problem that we face, and now what we need to do is impose certain restrictions on the structural parameters so that we can actually recover or find out exactly what is the value of those structural parameters. Okay, so one typical approach which is used is to use a recursive system that was proposed by Sims, okay, 1980. So Sims, if you recall from what I had said in the previous class, this is Christopher Sims, who's also received a Nobel Prize for his work on VAR models. Okay. So he had done a lot of work for the development of VAR models itself. So he has proposed this recursive system, and that can be used to identify the structural model to help us to recover estimates of all the structural parameters that are there in the structural model. So one thing that we can do is impose a particular restriction on the primitive system and set b to 1 equal to 0. Okay. So if we set b to 1 equal to 0 and we rewrite equation 1 and 2 using this restriction, we'll get these two equations, equation 12 and equation 13. Okay. Now, can anyone tell me what, if you're interpreting these two equations, how will you interpret it now? Anyone? By
So, ma'am,
setting,
as you mentioned,
yeah,
sorry,
go ahead.
ma'am, as you mentioned earlier, that the indirect effect will be eliminated this way. The EYT effect will be eliminated.
On, you're
ZT.
correct. Okay, on ZT. Okay, yeah. Any other way of stating the same thing? You're absolutely right, but I want you to state it in
The
a slightly
contemporaneous
different.
effect that the term we used is
Yeah.
no more there.
Okay, yeah. Okay, so here if you look at equation 13 now, YT does not have a contemporaneous effect on ZT anymore. Okay, it is only ZT that has a contemporaneous effect on YT. Okay, so this is the difference that we have created by setting this restriction B to 1. Okay, I hope this is clear to all of you. Now similarly, using this again, if you use the same approach, okay, so here this has been slightly simplified, you'll see it a little later here. Okay, so if you do the same thing with equation 12 and 13, which is basically to shift this term to the left hand side, and then rewrite equation 12 and 13 using matrix algebra. Okay, so if you use those techniques, then you pre-multiply the equation with B inverse, which is what we did earlier. Then here you'll be multiplying B inverse into epsilon t, where epsilon t is basically the vector of these structural error terms. So once you do that, if you multiply it out and find out what are the error terms in your var model in the standard form. Okay? I'm trying to make it as simple as possible. I hope you're not getting confused. So if you try and figure out what are the error terms in your var model in the standard form now. So E1t, if you multiply it out, B inverse into epsilon t, this is what you'll get, epsilon yt minus B12 epsilon zt. And here E2t will simply be equal to epsilon zt. Okay. So here you can see how important this sort of restriction becomes. Okay. So before I explain why this restriction becomes so important when you look at the regression residuals or regression error terms, okay, let's just look at these equations. So imposing this restriction results in an exactly identified system. Okay. So when we are saying exactly identified system, it means that you will be able to get the estimates of all your structural parameters now if you use the var model in the standard form. Okay. So now B inverse will be given by this. Since you have set B21 equal to 0, okay, your B inverse matrix will be equal to this. And pre-multiplication of the primitive system by B inverse now gives you this set of equations. Okay, again we've used matrix algebra here. Okay, generally when you're dealing with more than one variable, we usually use matrix algebra because it helps us to get a more compact representation. Okay. So here if you multiply this out, this is what I was talking about, you'll be able to find out what is E1t and E2t. Okay. Can I move on to the next page? Here we are just multiplying out these terms, all right?
Yes, ma'am.
Okay. Okay, so now this is your var model in the standard form. Okay. So here if you look at these, we've given you exactly what each of these coefficients is equal to. So for example, A1 naught, which is the constant term here, is equal to this. Here you're pre-multiplying B inverse into A naught. Okay, this is how you're getting this. Okay, so we've given exactly what each of the coefficients are equal to. Later on, you can try and do the pre-multiplication yourself and see whether you're getting the same results. Okay. Now, since B21 is equal to 0, this is the restriction that we have imposed. E1t is equal to this, and E2t is equal to the structural error term itself. Okay. So this is the beauty of this particular restriction now. What you'll notice is that E1t is composed of both the structural error terms epsilon yt as well as epsilon zt. Okay, but E2t is now simply equal to the pure structural shock or the structural error term. Okay, so what you will find is that in your second equation here, okay, which is zt. Okay, so zt will simply be affected by only shocks to epsilon zt here. Okay, it will not be affected by any shock to epsilon yt directly. Okay, of course, epsilon yt will appear here in yt minus 1, but that is an indirect effect again. Okay, but if you're looking at the direct impact of the structural shocks on zt, you'll find that only shocks to epsilon zt will affect zt here. Okay, no shock to epsilon yt will affect zt directly. Okay, whereas shocks to both epsilon zt as well as epsilon yt will affect yt now. Okay, so that is the difference when you look at this restriction which has been imposed, what difference that makes to the entire system of equations. Okay, now as a result of this, you'll find that variance E1, okay, is equal to this, variance E2 is equal to this. Okay, they're again constant. because of certain assumptions that we made. And covariance E1 and E2 are equal to this now. Okay. You can try and derive this or check this later for yourself. Okay. So now because of this, we now have 9 parameter estimates. Okay, you have the two intercept terms, then the coefficients associated with your predetermined variables or the lagged variables, then variance E1, E2 and covariance E1 and E2. So there are now 9 parameter estimates from your VAR model in the standard form. Now that you have imposed the restriction B21 is equal to 0. Okay? And that can be substituted into the 9 equations above to simultaneously solve for each of these structural parameters. Okay? So which are the 9 equations above? You have all these equations. Okay? You have equations for this, this and this. Since you can clearly see that you're able to directly get the structural parameters from these three, you don't really have to bother with it. Okay? But for the rest, you'll clearly be able to get the structural parameter estimates now from your VAR model in the standard form. So you can simultaneously solve for each of the structural parameters and find out their values. Okay? You will also be able to get estimates of the structural variances, okay, or the variance of the structural error terms. Okay? In addition to this, you will find that you can also get estimates for the structural shocks or the structural error terms, epsilon yt and epsilon zt. So how exactly can we do this? If you look at these two equations, since E2t will directly give you epsilon zt, okay, so there's no work that you need to do here. You can directly get E2t from the regression results. Then after that, since you will be able to find out what is B12, okay, and you already have epsilon zt, you can easily find out what is epsilon yt, since you will also know what is E1t from your regression. So you can easily recover the structural error terms or these sequences from your regression results. Okay? I hope this is clear to all of you, how imposing that restriction helps us in recovering the structural parameters. Any doubts or questions?
Ma'am, so then we can't use VR models when shocks in ZT affect shocks in YT affect ZT.
Shocks in YT? No, the thing is you
Oh,
will have to impose a restriction in order to
yeah.
identify the system.
We will have to. So in case if for example shocks in YT do affect ZT, can we
Yeah,
impose some other restrictions on some other parameters? Because
yeah,
mathematically speaking, we just have to reduce one of the variables.
yes.
So it
So
can be any other variable, right?
yeah, so basically either B12 will have to be equal to 0 or B21 will have to be equal to 0. One of those two will have to be equal to 0 so that you can actually recover your structural parameters.
And ma'am, if we like instead of B12 or B21, what if we set some other parameter to a constant value? Mathematically, would that make a difference? For
Uh,
example, if we say one of the coefficients is zero, like for example that
for
way.
the lagged variables, you're saying?
Yeah.
The idea is generally to impose restrictions on those contemporaneous variables, all right? Because your
Yes, ma'am.
lagged variables, later on
Lag
I'll
variables
discuss.
will be available to us, so contemporaneous variables will not be. I
Yeah,
get that.
and
Okay.
the basic problem crops up because your structural error terms will be correlated with the regressors.
Yeah, so our variance of estimates will be very high.
Yeah, you won't be able to use OLS at all, okay, in that
Yes,
case.
ma'am.
So,
Ma'am, I had
because of,
another question.
yeah,
How exactly are VAR models different from simultaneous equation models?
yeah, that is a good question. So, have you all studied that?
Uh, I no, ma'am. I don't think we were taught in Google simultaneous equation model.
Okay, so for simultaneous equation models, you again have a system of equations but there you're not looking at, it's not necessarily that you're looking at feedback effects or anything like that. Okay, so probably towards the end of this entire semester, maybe I'll try and go into that. It will be a huge digression if I get into that right now. Okay, but you
Okay.
might not necessarily be looking at feedback effects. Again, it might be based on theory, but you might not be interested in the fact that one variable is having a feedback effect on another. Okay, so that would be one simple difference there. And there are other techniques for estimating those simultaneous equation models. For example, you have 2 SLS, 3 SLS, and so on. Okay.
Yes, ma'am. Got it, ma'am. Thank you.
All right, so it is 3:32. So we'll just break for 5 minutes and come back. All right. So we'll meet at 3:37. If you have any doubts or anything, I'll address it at that point of time. Right. So I'll see you in 5 minutes. Okay, I hope all of you are back. Continue the class. Okay, so just a moment. All right, so in equation 13, okay, we had imposed this restriction that B21 equals 0. Okay, so that means that Yt does not have a contemporaneous effect on Zt. Now in 14, this is what I've explained earlier. I'll just read it out. This implies that both epsilon Yt and epsilon Zt shocks affect the contemporaneous value of Yt, but only epsilon Zt shocks affect the contemporaneous value of Zt. Okay, so this is how decomposing the shocks or the error terms actually helps us. Now the observed values of E2t are completely attributed to pure shocks due to the epsilon Zt that affect the Zt sequence. So you can see that once we actually used this restriction and found out what B inverse is, E2t was equal to epsilon Zt. Okay, so this, because of this restriction now, E2t is completely reflecting what happens to the structural shocks or the structural error terms. And these will be affecting the Zt sequence, okay, directly. Whereas epsilon Yt will not be affecting the Zt sequence. So decomposing the residuals in this triangular fashion is called a Cholesky decomposition. Okay? So this term is something that you might come across very often for VAR models. So whenever you impose a restriction on one of the contemporaneous variables this way, in our case we have restricted B21 equals 0, okay? It ends up having an effect on the residuals. So if you look at the matrix here, let me just go back to this. Okay, I think it's on page 7. Yeah. So if you look at this matrix here, this is your B inverse matrix, and basically when we are finding out what is E1t and E2t, you're basically doing this decomposition of the error terms, actually. The structural error terms, you're actually imposing certain restrictions on them also in the process, because of which you get this lower triangular matrix of zeros generally. Okay, so this is called a Cholesky decomposition, where your upper triangle will have certain elements, but the lower triangle will be a series of zeros most of the time. If you have n variables in your VAR model, you will have a larger number of zeros. Okay? So this is called a Cholesky decomposition. Okay? Now in general, you'll find that in an n variable VAR, your B matrix will be an n by n matrix. Okay? Since there are n regression residuals and n structural shocks. Okay? So there will be n such E1t, E2t terms, okay? And n structural shocks will be there. Now exact identification requires that n square minus n by 2 restrictions be placed on the relationship between the regression residuals and the structural innovations. Okay? So here we are discussing the restrictions in terms of the relationship between the regression residuals and the structural shocks. So you will have to place exactly this many number of restrictions on the relationship between the two sets of residuals here. Okay? So in our case, since it was a bivariate VAR model, okay, you will find that basically there are two regression residuals and two structural shocks. So your n here is basically 2. So when you're finding out how many restrictions you should be imposing, this will be 4 minus 2, which is 2 by 2, which is 1. So that's why we have placed one restriction. So depending on how many variables you have in your VAR model, you'll be able to find out using this formula exactly how many restrictions you should be placing on your VAR model so that you can actually identify the structural VAR model. Okay? I hope this is clear to all of you. So since the Cholesky decomposition is triangular, it forces exactly n square minus n by 2 values of the B matrix to equal 0. Okay? So you will be imposing restrictions on the B matrix itself Okay, so that's why I had said you will be restricting the contemporaneous relationship there. Okay, so here you will be imposing exactly these many number of restrictions based on how many variables you have in your var model. Okay, so whenever you're estimating the var model, what you can do is, since your right hand side variables, if you look at the standard var model, let's see if it's over here. Yeah. So this is your var model in the standard form that you will be estimating. Okay? Now, if you observe carefully, the right hand side variables are actually identical. Here you have yt minus 1. In both equations, you have zt minus 1 appearing, and there's no other variable appearing. Okay? So since they have identical right hand side variables, you can always estimate such models whenever you have identical right hand side variables and you have a system of equations. You'll be able to estimate your model using OLS. Okay. Now, in the case where suppose you wanted to drop one of these, okay, for let's say you had 2 lags of YT, okay, and 2 lags of ZT now, and suppose you found that you don't want to include the second lag of ZT, for example. So in that case, there's another technique that you can use called seemingly unrelated regressions. I'll try and explain that at the end of tomorrow's class. Okay. So that is a technique that you can use if your right hand side variables are not identical. Okay. So it's called SUR, or seemingly unrelated regressions, and the model is also called a near var in that case. Okay. It's not called the standard var, instead it's called a near var. So ideally you can go ahead and use OLS if your right hand side variables are identical. And remember, I said that it does not really matter if your coefficients are insignificant, since we are not really interested in the values of the coefficients. Most of the time you will find that since you're including a large number of variables in estimation, it's very likely that there will be a problem of multicollinearity, okay, in which case your coefficients will end up being insignificant. So it does not really matter, or don't bother too much about the fact that they are insignificant. Instead, we rely on certain other tools, okay, which help us understand how shocks affect the entire system of equations and how shocks affect individual variables within the system of equations. So these tools that we use are known as impulse response functions and also variance decomposition. So first we'll deal with impulse response functions, and then we'll move on to variance decomposition. Okay. So this tool that we're discussing, in order to actually understand what it is, first we need to rewrite the vector autoregressive model in the form of a vector moving average. Okay. So try and recall how when we were discussing ARIMA models and you were solving difference equations, okay, you found that generally your solution to a difference equation basically expressed a particular variable or a time series in the form of its lagged error terms. So it was expressed in the form of generally some mean value, and then you had the moving average error terms. Okay. If you go back and look at your notes from ARIMA models, you'll find that that was the general expression for a solution to a difference equation. Okay. So just like every autoregressive model, okay, will have a moving average representation. So that would have been called the moving average representation of an autoregressive model. So similarly, if you have a vector autoregression, okay, that will also have a moving average representation. Let me know if you're not following at any point. Okay. Now the VMA, or vector moving average representation of a VAR model, okay, is a very important feature of, again, the methodology introduced by Sims in 1980. Okay. So this representation, when once we rewrite the var model in terms of the error terms basically in the model, it allows us to actually find out what happens if there are shocks, okay, or if one of the error terms changes by 1 unit, or there's a shock to any one of these variables, how it changes or evolves over time in response to the shock to the error term. Okay. So the vector moving average representation actually helps us to trace the time path of the various shocks on the variables contained in the VAR model. Okay, so again we are rewriting the VAR model in standard form. Instead of using those equations, we are writing in the form of, we are using a matrix representation of the same VAR model. Okay. Now in the vector moving average form, we may rewrite equation 15 in this way. Okay. So basically, if you take those two equations, for yt you had this equation, right? Okay. This yt was equal to a1 naught plus a11 yt minus 1 plus a12 zt minus 1 plus e1t. Okay, so that was your equation for yt. Now, if you solve for yt, okay, solve it as some sort of a difference equation, and you try and express it in terms of solely the error terms. So basically, you will be iterating backwards and then solving for yt and finding out what yt is equal to. So similar to what we did when we were studying ARIMA models, you'll find that yt is equal to some mean value basically, and then you have the vector moving average error terms coming into the picture. So you'll have the cumulative sum of the error terms entering the equation. Okay, so this will basically be the vector moving average representation or form of the VAR model itself. Okay. So instead of this, the VAR model in the standard form, we are simply writing its vector moving average representation this way. Okay, so here you have the mean values, and here you will have the cumulative sum of the error terms basically. Now, if you try and expand this, please stop and ask if you have any doubts or any questions.
Ma'am, could you repeat from VMA?
Yeah. Okay. So try and remember when we were studying ARIMA models, okay, you were solving for yt by iterating backwards, right? Okay,
Yes, ma'am.
so you used to find out yt plus 1 is equal to a naught plus a1 yt plus et plus 1 and so on. Okay, this way you were iterating backwards and then solving for yt. So finally, when you solve for yt, let's see if I can try and go back. Okay, just wait for a minute. Yeah, so when you were doing this whole process, okay, so if you keep iterating backwards, what you'll find is finally yt is equal to some mean value, okay, this whole part, plus these moving average error terms, okay. So we are doing the same thing now with the VAR model. Okay, I haven't written out the equation because it might become very confusing for you all since it's usually in the form of a system of equations. So basically all you need to understand is you're doing the same process. You're taking yt and then iterating backwards and finding out what yt is equal to. So it will basically be equal to some mean value, which will be this set of terms, okay, and it will be having some moving average component of the error terms. Okay, is this clear to you?
Yes, ma'am, getting it.
Okay. So we're doing the same thing here in the var model. I haven't done the derivation because it'll be a bit mind-boggling for y'all, okay? So again, we're doing the same thing here. Just think that this is the mean value, okay? And this is the moving average of, these are the moving average error terms. So basically, once you multiply it out, you'll get yt is equal to y bar plus summation a11. Okay, this extra one should not be here. It'll be a11 into e1t minus I. So there'll be various lags of e1t basically. And then you will have plus again summation I is equal to 0 to infinity a1 to e2t minus I. Again, you'll have various lags of e2t. Okay. So this way you'll have these moving average error terms entering the picture here. Okay. I hope it's a little clearer now for you. Now further, if you use the fact that E1t and E2t are equal to this. Okay, remember earlier what we did was multiplied B inverse into epsilon t. That made the vector of the structural error terms. So we were multiplying B inverse into epsilon t. This is basically your epsilon t, and this whole thing is B inverse. Okay, so we are using the fact that E1t and E2t are equal to B inverse into epsilon t, and we can rewrite these equations again slightly. Okay, so you can rewrite equation 16 using 16 and 17. You can rewrite it in this way. Okay, so instead of E1t and E2t, we've simply put this right hand side of equation 17 now. Okay. I hope this is clear to you all. Any doubts or questions? It's just a manipulation. Just go through equation 15, 16 and 17. Okay, in this last equation, what we have simply done is instead of E1t and E2t, we've simply put in this right hand side of equation 17. Okay, so this is basically the vector moving average representation. Okay, and we are expressing again the var model now in terms of the structural error terms. Okay, now we can further simplify this expression that you see above by defining a particular matrix called phi I, okay, which has the elements phi j k I. I'll share these notes with you all in case you all are finding it a little too much to deal with right now. Okay, so we can define this 2 by 2 matrix phi I, which has these elements phi 1 1, phi 1 2, phi 2 1, and phi 2 2. Okay, so instead of this entire thing, okay, instead of this entire thing over here, we are simply defining this matrix phi I. Okay, so because of this, the VMA representation or the vector moving average representation of 16 and 17 can be written in terms of the structural shock sequences, okay, or the structural error terms. So here yt is equal to again their mean values plus, instead of writing this whole cumbersome term here, we are simply simplifying it to phi 1 1, phi 1 2, phi 2 1, and phi 2 2. Okay. If you multiply it out, you will be able to find out exactly what these terms are. Okay. Or again, if you want to express it in a more compact form, you can denote this vector again by xt, this vector by mu, the vector of means by mu. Then instead of this matrix, we can denote this entire matrix by phi I. Okay, that's how we are designating the matrix. And the vector of the structural error terms is denoted by epsilon t minus I. Okay, so far are you all with me? Are you all able to follow?
Yes, ma'am, I get it.
Okay. I'll share the notes, okay, and if you want me to, I will share the derivation part also, how exactly you got this VMA part from this, okay. Those who are
Yes,
interested, I
ma'am.
can share
Can you
it.
please share the derivation?
Okay, but it won't be in exactly that form, okay. So I'll
Yeah, ma'am.
try,
I'll make sense of it.
yeah, okay. So the VMA representation helps us to understand the interaction between the YT and ZT sequences. Now, how exactly will we be able to do that? Using these impulse response functions. Now, each of these coefficients in this matrix, that is 511, 512, okay, all these coefficients are known as the impulse response functions. I'll tell you exactly why in a moment. Okay. The coefficients of phi I can be used to generate the effects of epsilon yt and epsilon zt shocks on the entire time paths of yt and zt sequences. Okay. Now the reason that we are writing this whole var model now in this form is we want to understand how any small change in the structural error terms. Suppose there's a shock to one of these structural error terms. When I'm saying shock, there's something which causes a small change in the structural error terms. Okay, that's what I mean. So if there's a shock to one of the structural error terms, how exactly is it going to affect yt, and how is it going to affect zt? These coefficients will help us to understand the impact of any small structural shock on yt as well as zt, and we'll be able to see how yt and zt evolve in response to these shocks over several time periods. Okay, that's why I is here in brackets. I will assume different values ranging from 0 to, if you're looking at 10 time periods, what is the impact of a structural shock for 10 time periods, then I will run from 0 to 10. Okay. So generally we let it run, the general notation is to let it run from 0 to n. Okay. So you'll be able to trace the impact of any structural shock for n time periods and see how yt is going to behave in the same time period, then in the first time period, second time period, up to n time periods in response to a particular shock. Sorry. Yeah. Okay. So we're on the 11th page now. Okay. So phi jk naught are impact multipliers, are what are known as impact multipliers. So here j refers to the row, k will refer to the column in the phi I matrix. Okay, I hope you all understand. So for example, phi 1 1 denotes the element in the ith row and jth column. Okay, first row and first column basically. So phi jk naught, if I have 0 in brackets instead of I, this is known as an impact multiplier. So it's basically telling you how a shock to the structural error term affects yt or zt in the same time period. Okay. So for example, phi 120, okay, in brackets 0 or not, is the instantaneous impact of a 1 unit change in epsilon zt on yt. Okay. So to help you, in case you haven't figured out why it is epsilon zt on yt, okay, just look at the equation again. Okay, so let me show you this. Okay, so phi 12 is appearing here in the equation for yt. Okay, so when you're multiplying it out, you will basically find that phi 12 appears in the equation for yt and not for zt. Okay, and since phi 12 will be associated with this one, okay, with epsilon zt minus I. Okay. So here if I is equal to 0, you're looking at what is the impact of a shock to epsilon zt itself? Okay, not any of its lags, but what is the impact of a shock to epsilon zt? How is it going to affect yt? Okay, is this clear to everyone? Okay, so epsilon 120 is the instantaneous impact of a 1 unit change in epsilon zt on yt itself. Okay, so you'll be looking at here the shock is in terms of a 1 unit change. So usually when you're estimating VAR models, you'll be looking at either a 1 unit change in the structural error term or a 1 standard deviation change in the structural error term. Okay, so here we are discussing it in terms of a 1 unit change in epsilon zt. What impact does it have on yt? That will be revealed by this coefficient phi 12 and in bracket 0. So we'll be able to understand what is the impact of a shock to epsilon zt on yt in the same time period. Okay, in time period t itself. Now, similarly, if you look at phi 111, okay, in brackets you have 1. Here, this is the 1 period response of a unit change in epsilon yt minus 1 on yt. Okay, so if you look at the subscript here, which is 1 1, so it's telling you what is the impact of a shock to epsilon yt. Okay, what is the impact of a shock to the structural error term associated with yt, epsilon yt, on yt itself, since the subscript is 1 and 1 here, but 1 period ahead. Okay, so what is the 1 period response of a unit change in epsilon yt minus 1 on yt? Okay, or another way to look at it is what is the effect of a unit change in epsilon yt on yt plus 1? Okay, so what happens 1 period ahead? If there's a shock to epsilon yt, how does it impact the time path of yt in the next period? Is this clear to all of you? Any doubts regarding the notation, how to interpret? Okay, I'll just check by asking you a question. So, wait, let's see. Okay, so can anyone tell me what phi 22 3 will represent?
Ma'am, it will represent the impact of
That was really fast. Phi
yeah
223. Okay.
yeah. So it's 2 2 3, right? 3 is in brackets, right?
Yeah.
So for example, if let's say 2 is z, then we can say it will represent the impact of the third error term of the z variable on z in time t.
Third
So
error term on the z variable.
so ez t minus 3
Okay.
impact on zt.
Okay. Correct. In the which time period?
Zt, ma'am, in the tth time period.
No, in the third time period. Okay.
Yeah.
Since I in brackets you have 3, right? So it will be the third time period. If I put 0 in brackets, then it would be in the same time period.
Yeah. Ma'am, just a doubt. The error term will be of the third time period, or will the z term on the left hand side be of the third time period?
See, you can do it 2 ways, which is what I've written there also. If you're taking epsilon zt minus 3, then here it will be the impact on zt. Okay,
Yeah.
in the third time period.
Yeah.
Then I think somebody's message, send a chat message. I'll check that in a moment. Then the other way to do it is if you're looking at the impact of epsilon zt, okay, no lags, on
Yes, ma'am.
zt plus 3 in the
Okay.
third time period.
So either way
Since
will
3
be
is,
correct.
yeah, either way will be correct. You can
Okay.
interpret it in these 2 ways. You both are correct. Okay, but stick to one
Excuse me, ma'am.
interpretation. Yeah, correct. Yeah, go
Ma'am,
ahead.
sorry, but could you please repeat the other second way that you just mentioned?
Yeah.
That
Okay.
ZT plus 31.
Yes. Okay. I'll just show you that page again.
Ma'am, the number shown in the bracket shows
Uh,
that we have to subtract t minus 3, for example, if there is 3. But what
yeah.
does third time period mean?
Uh, See, basically, the shock happens in time period t. Okay. Then you're seeing what is the effect of that shock on either yt or zt at time t plus 1, at time t plus 2, and so on. Okay. So you're seeing exactly what is the impact of a shock in various time periods. Up to n time periods, you can trace the impact of a single shock and see how it's going to affect the time path or the behavior of yt or zt. So uh, just give me a moment, okay? I'll come back to your question. That was, I think, Ayush, right? I'll just come back to what you were saying, okay? Yes. So what somebody was asking is, I asked you 5, 2, 2, 3. Okay. So I'm just repeating for everyone's benefit. So there are two ways to interpret this now. Okay. So if I say 5, 2, 2, 3 in brackets 3. Okay. So basically I'm saying that I'm interested in what is the impact of a 1 unit change in epsilon zt, okay, on uh, zt plus 3, okay, 3 periods ahead. Okay, in the third period, what is the impact of a 1 unit change in epsilon zt on zt plus 3? Okay, so I'm seeing what is the impact of a 1 unit shock to the structural error term after 3 periods, okay, or in the third period. Same way to say it. Or the equivalent way, the second way of looking at the same thing is, if there's a 1 unit uh, change or shock to epsilon zt minus 3, okay, then what is its impact on zt in the third time period? Okay, I hope you've got it now.
But ma'am, when we are putting the value of I equals to 3, then
Yeah,
as per the equation that you have mentioned, how are we getting zt plus 3? I mean, I understand that both means the same, but if we
yeah,
just go by the equation, then
yeah. If
aren't
you
we supposed to write zt minus 3 in the first equation itself?
yeah, see, when you're doing this, that might be slightly problematic. Okay, so uh, one thing I can, one way I can rationalize it or explain it is, when you're dealing with impulse response functions, generally you'll be looking at a 1 unit change in epsilon zt, okay, and then basically you'll be looking at a graph, okay, which will plot these coefficients over various time periods. So along the x-axis, you will have the various values of I, which ranges from 0 to n. Along the y-axis, you will have the value of your yt or zt variable. Okay. So basically, you will be drawing a graph and seeing what is happening to yt after a 1 unit change in epsilon zt. So there, when you're using the graph, you can use this interpretation that you're looking at the impact of a 1 unit change in epsilon zt on zt, then zt plus 1, zt plus 2, zt plus 3, and so on. Okay, so there it will make sense to you. Okay, if you'll just look at the equation, you're right. It may not, it may seem like it's incorrect, but it's essentially the same thing or it's equivalent. Does that answer
One
your
more thing,
doubt?
one
Yeah.
more thing, ma'am, that
Yes.
when we are writing this with t minus I here, so
Hmm.
then we are saying that we are moving 3 periods back, like that. Am I right?
The, yeah, error 3 periods ago. Yes.
Uh, then, ma'am, are we trying to interpret the result of present shock on the previous period like that? Because
Present shock
we are
on.
calling it a 1 unit change in uh, ET.
Hmm.
So, are we trying to say that the previous, or we are saying that the previous shock on the present period? Like, I'm confused between the two.
Okay. Let me think about your question and I will answer you tomorrow, okay? Because, see, generally, what you would have found even in your, when you're doing your empirical work, you're basically working with one column of numbers, right? And then from that itself, you're taking the lags and the leads and so on. Okay, so I will have to think a little to kind of word it in such a way that I don't say something incorrect. So let me think about what you've asked and then I'll answer you tomorrow. Okay.
Yes, ma'am. Thank you.
Ma'am, I had another question.
Yes.
These two interpretations basically would only be the same or would only be simultaneously correct if both these, if the variables we are looking at are stationary, right? So
Yeah.
if we look backwards from time or if we look forwards into time,
Yeah.
the series is the same.
Yeah. So whenever you're estimating a VAR model, generally you make sure that your variables are stationary and then do the estimation. Okay. So yes, they have to be stationary. Ayush, what was your question again?
Ma'am, my question was that when you said about the question 522 bracket 3, so
Yeah.
so we said that impact of epsilon zt minus 3 on zt at
Yes.
third time period. So
Yeah.
I wasn't able to get the meaning of third time period because the 3 in the bracket we already accounted it for in epsilon t minus 3. So what does third time period mean?
Uh, okay, to give you a very non-economic example, suppose uh, l- this is the only thing I can think of at this moment. Please don't think that it reflects something about me or whatever. But just think that if somebody comes and punches my face, all right? So the impact on the first day, okay, for first day generally the bruise might not show up very badly, and on the first day my face will look a certain way. Okay, so just imagine that I'm taking pictures of my face over a period of 10 days now. Okay, so the first day, what is the impact of that punch on my face? Okay, that gives you 5220. Okay, then the second day, maybe it's looking really black and blue. Okay, and that is the impact on the second day. Okay, so basically you're looking at what is the impact of this one event or this one shock on the same variable at different point of time. So if you take a snapshot of my face on the third day and I show it to you, that will be the impact at the third time period. I hope you're able to understand now.
Yes, ma'am, got it.
So basically, even if you think of something like COVID, okay, so when the pandemic first hit, you would have found that it would have affected GDP with some lag, right? You wouldn't have seen the impact immediately. You would have seen the impact with some lag. Okay, so the same way, you'll find that the impact at time period 0 will be a certain value. Okay, GDP will assume a certain value. Then in the first time period, it will assume a different value. Second time period, the impact of that shock will die down, or it will reflect in GDP very slowly. Okay, so we're basically tracing the evolution or the impact of a particular shock over various time periods. I hope that answers your question.
Yes, ma'am.
Ma'am, um,
Yes.
the example that you just now gave of this punches, is it in line with the equation that you have shown to us? That ET, I'm sorry, the equation was, could you please just show the picture?
Yeah, just 1 minute. Okay, wait. This thing keeps popping up, so I'm not able to. Yeah. Okay, I'll have to figure out a way to beat that. Let me just close this and see if it comes now. Okay, I think I'm too slow. Okay, let me just open it again. It's taking too long. Yeah.
Yes, ma'am. So in this equation that we have written, like zt minus 1. So
Hmm.
the example that you just gave, is it in line with this equation? Or
I think you're
are we
coming back to the same question, Rashi, which I will answer tomorrow. So
because now
basically,
I'm still confused with the fact that are we taking t minus I as the progressive or the regressive way? Like, are we talking about the forward period? Because in the example that you gave, we are talking about the forward periods. However,
see,
I was interpreting t minus I as the backward time.
one thing that you should understand is, since this whole thing is there, right? It's summation of this. So probably if I'd completed this whole part, you'd have understood better. So I assuming various values. Okay, I can be 0. So then you're looking at the impact of a 1 unit shock on epsilon zt itself in the same time period. Then I will assume the value 1. Okay, so after one time period, what is the impact of that shock on zt?
Yeah, that
Are
was
you
the
able
word
to
I
get
was
it
looking
now?
for. That you are saying that after. I was actually looking for I was thinking it as before, like I interpreted it wrongly. I'm sorry
Since
for that.
no, it's fine. It's a good point because others might have the same doubt. So here, since I is assuming various values, no, so this will keep changing, and you'll see the impact of a 1 unit change in epsilon zt on zt, yt, and so on. I mean, since we're talking about phi 2 2, it will be on zt itself. Okay, so uh, zt itself on zt in the same time period, if it's 0, then if it's 1, then after one period, okay, what is happening? Again, after one period, epsilon zt would have become its lag, right? When you're looking at the value of zt. So that
Yes,
way you
ma'am.
can
Now I got
interpret
it.
it. Okay. It might seem
Yes, ma'am.
slightly confusing, but it's good that you're asking these questions because it clarifies things for everyone. Okay, it's 4:20. I'll quickly try and finish this portion. Okay, just this part about impulse response functions. Yeah, okay, so these are two equivalent ways of looking at the same thing. Now, the accumulated effects of unit impulses in EYT or EZT can be obtained by appropriate summation of the coefficients of the impulse response function. Okay, so to explain this, it's better we look at the next part, the example. So after n periods, you'll find that the cumulated sum of the effects of epsilon zt on the yt sequences the sum of all these terms. Okay, summation phi 1 to I. Okay, so if you're looking at n time periods, what is the impact of a single shock on epsilon zt, which means a 1 unit change in epsilon zt? What is the impact of that on the entire yt sequence? You'll simply be adding up the impact over those n time periods. Okay? So you'll be summing up these coefficients basically for time period 0, 1, 2, and so on up to n. Now, if you let n approach infinity, it will give you the total cumulated effect. Okay. Now, this is what I think Govind was mentioning. Since yt and zt sequences are assumed to be stationary, it must be the case that for all j and k, phi jk square, okay, I is finite. So if you find out the cumulated sum of the impulse responses basically and square them, okay, you will find that that is finite. The sum is finite. Okay, since these variables are stationary, basically what it means is after n periods or after a certain number of periods, you will find that the impact of that shock basically dies out. Okay, the shock will not persist forever and ever. The impact of that shock will die out slowly, gradually, and yt and zt initially they might deviate from their long run mean value, but eventually they will come back to their long run mean value since they are stationary variables. Okay, I hope this is clear to all of you. Then the four sets of coefficients are called the impulse response functions. Your phi 1 1, phi 1 2, phi 2 1, and phi 2 2. They're all impulse response functions. Graphical plots plotting the coefficients of phi jki against I depict the behavior of yt and zt series in response to various shocks. So these IRFs or impulse response functions are basically graphs which will have, like I mentioned earlier, along the x-axis, you'll have the various time periods. You'll be plotting I, which is your various time periods along the x-axis. And along the y-axis, you will have what is the impact of these shocks, or what are these coefficient values against I, okay? And that will help you understand what is the behavior of yt and zt in response to various shocks. So we'll try and look at some IRFs tomorrow to help you understand better, okay? So today's class, we'll end it here. I just wanted to give you some feedback on your assignments before we stop. Any doubts or questions?
Ma'am, one thing.
Yes.
The whole we studied, like, can you just give one example of the real life terms, economic terms, that we can say that they are connected this way, that we saw in equation 1 and 2 itself? Like, I can think of only expenditure and income factor, where we can say that, like, our expenditure is YT, then it is dependent upon income. Similarly, our income is dependent upon the expenditure, like that.
Yes. Okay.
But
Yeah.
is there
Apart
any? Okay.
apart from that, you have GDP, money supply, okay, then investment, okay, all these things, your
Yes, ma'am.
basic macroeconometric models itself, but you can incorporate additional variables like what do you say, money supply, what is the impact of that on GDP. Then many models will have exchange rates, they'll have the current account. So you could have a whole series of variables. For example, how does the GDP variable affect the current account, then, or imports and exports, okay? So all these things, your basic, most of the time var models are used for macroeconomic purposes itself. So if you take most of these macroeconomic variables, you'll be able to fit var models to help you understand various macroeconomic theories.
Yes, ma'am.
Okay. Tomorrow I'll try and give you all some more examples for this. Okay. Not just for var, but few other topics we'll be studying tomorrow. I will stop recording at this point. Okay. So I'd like to give you feedback on your assignments. Did I stop? I don't know.